Hello friends, welcome to another video in random variables. We'll discuss continuous random variables today. We've finished our discussion for PDF and CDF for discrete random variables. Let's understand various examples of random variables. Then we'll do a numerical on the probability distribution function of a random variable. And after that, we'll do the CDF of random variables. Now, a continuous random variable would be a random variable that will have value of probability at each point ranging from -infinity to infinity. Although most of the points in that range will have a probability of 0, because if you, let us say, want to plot the probabilities of temperatures in June, then what you could do is, on the horizontal axis, you could take temperature, and you would see that the probability of a temperature of around 45 degrees would be pretty high. Let us say we keep it as 60%, right? So this is going to be 0.6 for 45 degrees, but for each value of the temperature, 45.1, 45.12, you'll have certain probability, and as you move away from 45 on both the sides, the probability is going to decrease. So you could maybe get a graph like this around 45 and having a temperature of, let us say, 17 degrees, or having a temperature of 60 degrees is most unlikely. So you'll get very small probability of that. And having a temperature in -20 degree will be 0. Having a temperature greater than 60 degree will also be 0. But the temperatures have probability throughout the range. So this is one example of continuous random variable. And another example of random variable that I've taken to discuss is the weight of a 20-year-old male. So if you were to calculate the weight or find the probability of a weight of a 20-year-old male, the probability of getting a weight around 65 kgs is pretty high. So you'll say that a 20-year-old male with a 65 kg weight is pretty probable. And then again, for each value of weight, you'll have some probability associated with it. So 70 kgs will have some probability, maybe 80 kg will also have some probability, but it'll be continuous in nature again. And you see that the graph is symmetrical about this value, which is most likely to happen. And this is, by the way, known as normal distribution, that we will discuss in the coming videos. Now, if we look at this function is also a continuous function because it has certain probabilities from the range of -3 to 2, and beyond 2 it has a probability of 0. So probability of let us say t greater than 2 is 0, and probability of t less than -3 is also 0. So if you get a question like this where the probability distribution function is drawn like a graph, then you need to know that the total probability of such a graph is 1. So you could say that from -infinity to infinity, this function f of t dt will be equivalent to 1. And because this function is defined only in the range of -3 to 2, so the area of this function will be equivalent to 1, because this integration will depict the area nevertheless. And then you could get questions like this, that you need to find the value of k, which is pretty simple. You could find it from this formula. We have done this for discrete random variables also, where the sum of all the probabilities of all the samples was 1. Here the total area of this function is going to be 1, because this is a rectangular function. So you could say that from -3 to 2, the width is 5 and the height is k, and this should be equivalent to 1, so k comes out to be 1 by 5. Once k is known, then everything falls into place. If you wish to find probability of t less than -3, which will be 0, anything less than 3 has a probability of 0. And if you were to find the probability of t less than equal to -1, then you need to draw a line at -1 here, and let's find the area of this portion of the rectangle. This will be 2 into k is 1 by 5, so this will be 2 by 5. So the probability of the random variable where t is less than -1 is 2 by 5. Then maybe you could get a question like this where you need to find the probability between 1 and 2.5. Then from -1 to 2.5, which is this, you need to find the probability, but you know that this area is 0, so you'll only find till 2, and the area from -1 to 2 is calculated as this is total length of 3 into 1 by 5, which is k, so this is going to be 3 by 5. Alright, and then you could be asked to find the probability for t greater than 1. For t greater than 1, we need to draw a line here and again find the area. This area is from 1 to 2, the width is 1 into 1 by 5 is equal to 1 by 5. And an important property of continuous random variables is that if you wish to find the value of probability at certain point equal to, let us say, 1, this will be 0. You could find the probability at a point greater than equal to 1 or less than equal to 1, but at certain point it is going to be 0 because you cannot find the area of the line, so that makes sense. And then maybe you could find probability of t greater than equal to 1.5. 1.5 will be somewhere here, so this is going to be 0.5 into 1 by 5, again very small quantity. 0.1 is the probability of such an area. So rest everything is pretty much the same as the discrete random variables, but the only point of difference is that at certain point, at a discrete point, the value of the probability is 0 for continuous random variables, and the area of the function should be equivalent to 1 because the probability of all the variables sum up to 1 only. This is all I wanted to discuss about continuous random variables introduction. I hope you liked it. If you did, give it a thumbs up. Consider subscribing. I'll see you around. Take care. Bye.